Hi everybody, welcome back to my channel on Feynman integration. Today we will be evaluating this integral, the integral from 0 to 1 of x minus 1 over quantity x plus 1 times natural log x dx. I got this integral from the channel Mathematics MI. I will try to remember to link to the video in the description. We will be expressing the answer a little differently than he did. It turns out the answer to this is the natural log of pi over 2. However, we'll be expressing it as a sum. And we'll be using two tools today. We're going to be using the fact that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n. And that's true on the interval -1 to 1, with -1 being included and 1 not being included. And you can see why, because if you plug in 1 there, you'll get 0. That's not going to converge. This is the interval on which it converges. Luckily, we have that. That's we have that interval, so we're good there. All right, so let's get started. Our first step, like always, is we are going to create a function of t closely resembling our original integral. So we'll have f of t being equal to the integral from 0 to 1 of x to the t minus 1 over x plus 1 natural log x dx. Okay, a couple things to note. If we evaluate our function f of t at the point 1, we will get back our original integral. It's going to be equal to I. Also, if we evaluate it at the point 0, we will get 0, because x to the 0 is 1, 1 minus 1 is 0, anything over 0 is 0. The integral of 0 over any interval is 0. So, f of 0 is equal to 0. All right. So I'm doing this without notes, so bear with me. Okay, let's see. The next step, of course, is going to be taking a derivative with respect to t of this, using the Leibniz rule for integration, for differentiation under the integral sign. Okay, so that would give us f prime of t is equal to, well, the same interval, 0 to 1, of the partial with respect to t of this integrand. And that will evaluate to x to the t over x plus 1. And I hope you can see why that would be. Because you'll get back a natural log x when you take the partial with respect to t of that x to the t, and it will cancel that natural log x, which is what we wanted. And this 1 drops out because you can split that up, and then this 1 over x plus 1 ln x is simply a constant with respect to t, so that would be 0, leaving you with nothing but this. Okay, so how do we proceed from there? That's not an integral that you would normally be able to do with, calculus 1 and 2. Well, actually, you would be able to do it with calculus 2 techniques, that's what we're going to be doing. We're going to be utilizing this fact right here. But if you've only gotten up to calculus 1, that integral would be impossible, unless you're really smart and we're able to figure out this whole mess right here. All right, so let's rewrite this using this. Okay. But it doesn't exactly match. We have 1 minus x here, and we have 1 plus x there. I'm going to rewrite that as 1 plus x just to make it a little bit nicer. 1 plus x. But you know that that can be written as 1 minus x minus x. Okay, so now we have it in the right form. So now all we need to do is, since this is minus x and this is minus x, all we need to do is plug in minus x for our x in our sum. So what would that give us? That would give us, this would be equal to the integral from 0 to 1. We'll leave the x to the t alone for now. And then we'll convert this 1 over 1 minus x into sum notation. So this would be the sum from n equals 0 to infinity of, let's see, that'd be negative x to the n. Negative x to the n. And then, of course, we'd have dx. Yep. So those two functions are equivalent, of course, on our interval, which we have that interval. All right, let's see what to do next. Well, instead of that negative x to the n, I'd like to write it this way. We'll write that as negative 1 to the n times x to the n. Okay, now what next? We're going to utilize this fact. I believe it's called Fubini's theorem, and it just states that you can interchange an integral and a sum sign under certain conditions. You just have to make sure that there's no problems with convergence, and in this case there isn't. So what we're going to do is, well, you know what? First, we can actually, what do I do with my eraser here? There it is. Since this doesn't depend on n, let's just bring it right inside our sum, and you can do that. This is just the sum of a bunch of stuff that is dependent on n, and then we have an x to the t, which is not dependent on n. All those terms would be multiplied by x to the t. So we just get x to the n plus t. All right. Now we'll use this. We'll use Fubini's theorem on this right here. So that will give us f prime of t is equal to the sum from n equals 0 to infinity. And let's see. And we're also going to have an integral from 0 to 1. All right. The integral is dx, so we'll leave all of the x terms to the right-hand side of the integral. So this would be the sum from 0 to 1, the integral from 0 to 1 of x to the n plus t dx, of course, with this negative 1 to the n on the outside of the integral. And I hope this makes sense to you. I brought that negative 1 to the n outside the integral because it's not dependent on x, so it's a constant with respect to x, so you can bring it right outside. Okay, all these terms do depend on x, so they have to remain inside. Okay, next step, we are going to evaluate this integral right there. So, this would make this, let's see, f prime of t would be equal to the sum from n equals 0 to infinity. Still have the negative 1 to the n. And let's just go ahead and evaluate that integral. We'll just put a parentheses right here. Let's see. That's going to be, let's do it step by step, just so I don't make any silly mistakes. Okay. This is going to be the antiderivative of this with respect to x, evaluated from 0 to 1. So this is just going to be times x to the n plus t plus 1 over n plus t plus 1, evaluated from 0 to 1. Okay, well, you see that if you evaluate it at 0, the whole thing's going to be 0, and if you evaluate it at 1, You will get 1 to any power is just 1. So we would just get 1 over n plus t plus 1. I hope I didn't make any silly mistakes. If not, if I did, you'll never know it because I would not post the video. So if you're seeing this video, this is correct. All right. Well, we've got f prime of t. So, how do we get f of t? We integrate. So, to save space, I'm just going to erase this prime notation right there. And let's just put an integral sign right there. An indefinite integral. And since that's t, this is going to be integrated with respect to t. Okay. Well, all right. Let's do a little manipulation here. This is still going to be negative 1 to the n. And again, let's use Fubini's theorem to interchange the integral and sum notation. All right. So we're going to have the sum of this integral. Yeah, there we go. Okay, so now all we do is evaluate the integral. Well, let's see, this negative 1 to the n is a constant with respect to t, so we'll bring it right outside the integral. Negative 1 to the n. I know this is very hard to read, but so be it. All right. Well, what's this? This is the natural log of n plus t plus 1. So we'll rewrite that. So we're going to have negative 1 to the n times the natural log of n plus t plus 1. All right. Right? Wrong. Plus c. Right? Because we did an indefinite integral with respect to t. So there's going to be a constant of integration. Well, how do we get rid of that constant of integration? We do it the same way we always do it. We know that f of 0 is equal to 0. So let's find our c. Okay. So that would mean... let's do this over here. F of 0 is equal to 0. That means that 0 is equal to the sum from n equals 0 to infinity of this thing where t is 0. So that's still going to be negative 1 to the n times the natural log of n plus 1. What's that doing there? Okay. Yeah, plus c. In other words, our c is going to be equal to the negative of the sum from n equals 0 to infinity of negative 1 to the n natural log n plus 1. Okay, so if we put this into that, replace that c with this, I hope you agree that we would end up with this. That we would get Negative 1 to the n times the natural log of n plus t plus 1 over the natural log of n plus 1. That's just basic properties of logarithms right there. So that's going to be n plus t plus 1 over n plus 1. We don't need that c anymore because we've already accounted for it. There we go. We have a function expressed as a sum that all we need to do is plug in 1 for our t and we will get our answer. So let's just do that. Let's plug in 1 for t and call it I. I'll rewrite it. I got some room. So that means I is equal to the sum from n equals 0 to infinity of negative 1 to the n times the natural log of n plus 2 over n plus 1. That's it. There you go. The channel that I got this from, Mathematics MI, he actually got like a real answer for it. It turns out it's this. It's the natural log of pi over 2. I think, I hope I'm remembering that correctly. I believe it's the natural log of pi over 2. Let me check that really quick. Hold on. Be right with you. What is the natural log of pi over 2? Yeah, that's it. That's what he got, and it turns out that it is equal to this. So that's nice in and of itself. He did it one way. He also used the Feynman technique, but you know, watch his video. He did it differently. He uses the gamma function and things like that. I might get into that later on in the channel, but for now, I think that's interesting. We got two different answers that are equivalent. So this is, in fact, equal to the natural log of pi over 2. So anyway, there you go. That's my video. I hope you enjoyed that.